So I'm now going to talk about linear regression and how we can solve it using a closed expression. And this is going to be for a one-dimensional case. So mathematicians already know very well how to find the maxima and minima of functions. And what you do, if you could write down a mathematical function, all we have to do is we say, okay, we've got the function, now let's differentiate this with respect to whatever it is we're trying to minimize it to. And then we set the differential to 0. And then we solve the equation so that we end up with the equation actually being true, right? So what this will do is it will locate regions where the gradient is 0, of course, and these correspond to maxima, minima, saddle points. In our case, we're just going to not worry too much about this. Since we've got nicely well-behaved quadratic functions, we're just going to say, well, we're just going to minimize this. And we're going to, when we set this thing to 0, we're going to end up finding the minimum. Now, we came across expressions for the error gradient with respect to the m parameter. And we found that we actually had the expression minus 2 sum across all data points, data point xi, multiplied by the y data point value minus mxi plus c. Similarly, we came up with a gradient with respect to the parameter c, the constant, which came out to be minus 2 multiplied by the sum across all data points of yi minus mxi plus c. So we've already got the gradient expressions, and what we did before is we just used them to use gradient descent. So we wanted to move down basically parameter space such that we moved down in the direction which minimized the error in terms of what we get arising due to the parameter m and what we get arising from the parameter c. Okay, so we had to do that. We had to calculate these things every time, and then we basically do an update on m and an update on c, and then we do, go round in a loop and iteratively try to find the solution to this. But we don't have to do it that way. What we could also do is we can say, let's do it, from the analytical perspective now, and see if we can write down an expression which tells us immediately what the answer should be. So what we're going to have to say is, when is dEdc equals 0? When is the gradient with respect to the constant equals 0? So we write down our expression minus 2 sum across all data points yi minus nxi plus c equals 0. When is that the case? And then we can just slightly rearrange this equation and multiply by, well, divide by minus 2 in order to get rid of the minus 2 factor. First thing we want to do then, basically we want to solve this equation for c. If we can solve this equation for c, we can say immediately what the constant is. So what does that going to involve? Well, let's first of all split the sum up. We'll leave the yi term on the left-hand side. So we've got to, basically we take the sum of just the yi term, and then we move all the rest of the sums onto the other side of the equation. So then we've still got the sum of, across all data points of m xi, and then we've still got the sum across all data points of c. Now you can see that if we add up c n times, that just goes to nc, because c is actually a constant. So we've already simplified that slightly. We've got rid of that sum. So we slightly rearrange, because we're interested in c, so we want to have c, a c term on the left hand side, and what's left on the right, well, we can then move the yi across, and we take away the m, well, the sum across mix, and we take the m out because it's a constant. Again, all we have to do next is just divide through by n, and then we have an expression for c. So 1 over n, sum across all data points yi, take away m, multiplied by 1 over n, sum across all data points xi. Now we notice that this 1 over n, sum across all data points yi, is simply the sample mean of y, right? It's the sample mean of the y values. So we can just write that as y hat if we wish. And this 1 over n sum across all xi's is just the sample mean of x. So we end up with a simple expression, c equals the sample mean of the y points, take away m times the sample mean of the x points. So that gives us a way of calculating c. The only thing that's a problem at the moment, though, is the fact that we don't know what m is, right? So if we did know what m is, we could just use that immediately. We just have to calculate the average of the y values, the average of the x values, and we'd be done. But now what we need to do is actually solve for m, and what we're going to end up with is a simultaneous equation. We're going to have one for c and one for m, and then we can basically substitute one in the other, and then have an expression that we can actually solve. In fact, we can solve both for c and both for m, just in terms of the data, and that's what we want. So what we do is we start off now looking at the expression for the error with respect to m, and we set that to 0. Sorry, the error gradient with respect to m, and we set that to 0. And just like we did before, we simplify it. We divide by -2, get rid of that term. We don't need that. And then again, we split the sum up. We notice this time then we've got a sum across the yi's, and they're multiplied by xi's. So we can put the sum. We can leave that on the left hand side, but we have to multiply this out. So yi xi, that goes on the left hand side, and then on the right hand side we're going to put all of this lot. So it's going to then be equal to sum across all i's, all data points, m times xi squared, because we've got xi there and xi there, plus sum across all data points cxi, right? Now what is it actually we're trying to get? Well, we're trying to work out what m is from this expression, so we want to get a term on the left hand side with the m in it. So we want this term in the middle here now on the left hand side. So on the right hand side, basically we've got to have this term here, the sum across all data points xi, yi, and then we'd have to take away this. So we take away sum across all data points c, xi, and we just actually put the factor c outside there because it's a constant. Right, so we've got our expression here, but we had an expression for c from before, right? We have the expression from c from before in terms of m. So what we can do now, if we substitute this expression for c into the c here in the equation at the top here, then we end up with an equation which is just in terms of m, in terms of xi, and in terms of yi, which is good. That means we can now solve this for m, and that's really what we're trying to do. So next thing to do is to collect terms in m. So we're going to take out m as a factor. We take that out here, factor here. We end up with an xi squared here. We have to take away, so it's basically on the other side. So we have to take this term, that cancels out that negative, and we've still got this. We've got this term here. So we've got this minus 1 over n. Sum across all xi's multiplied by sum across all xi's here equals what's left. So we've got this term here, the sum across all data points xi, yi, and then we've got this term here, take away 1 over n, sum across all data points yi. And of course, we've got, having got that expression, the next easy step is just to divide both sides by this term which is following the m, and then we have an expression for m. And the good thing about that, is we can directly calculate this from the data, right? We can calculate this product of the two terms summed across all values. We can calculate these values as well. This is the sum across all i's, sum across all y's, so all x's and all i's. So basically, we can calculate the whole of this just on the basis of the data. Now, given the fact that we can calculate m in that way, you could do that numerically and you come up with a single value. And if you've got that single value, you can then put that value in here into the m expression term for calculating the constant. So you wouldn't have to substitute anything else after that. If you're doing it computationally, you just work out m and then you put it in this equation, and then you can get c by doing these calculations. If we did actually substitute m in, which is a little bit messy, then we'd end up with this overall expression for calculating c just on the basis of the data, and where this term here obviously gives us what the m is, right? But again, if you were doing this numerically, you'd probably first calculate m like you did on using this expression, and then you wouldn't have to do the calculation again. You just use the value here and then stick it into this equation. So that's doing it all from first principles, and first principles is very important to understand because, first principles is really what's going on with this kind of algorithm. It's particularly also interesting to understand these things, because understanding linear regression is a nice stepping stone towards understanding neural networks. Now, of course, Matlab's got lots of functionality built in, and one of the things it gives you is a regression function, which is a general multidimensional regression function. So let's have a look at using that, just to sort of give you a feeling of what you can do with that. So let's imagine we're going to generate some test data, right? We're going to generate a line ax squared plus bx plus c using various coefficients for a, b and c, and this is going to give us a curve. What I'm going to do now, I'm going to sample x, so that's basically the x values, and this is then going to give you the corresponding y values. I'm just going to use the line space command. Effectively, this just lets you generate so many values, stepping through values from the starting to the end point. I'm also going to add a bit of noise on as well. So let's just very quickly show you what I'm doing there, just to give you an idea. I'm just saying we've got 100 samples. I'm just going to say that the x values are going to have a starting and ending point of -4 to 6. I'm putting in my coefficients here as well. I'm just generating a set of x values between the starting and ending points, and in fact I want 100 of them. I'm then going to pop these x values into my quadratic computation, which is going to implement this line here. I'm adding a little bit of noise on, and when you do that you end up with a quadratic curve like that. So it's a noisy quadratic curve, spans -4 to 6 on the x-axis. Now, what we can do with the regress function is we can actually fit a linear basis, it's called. So we're going to fit effectively mx plus c is what we're going to fit. And in order to do that, we have to generate a basis function which uses the x data, because we want the coefficient of the x, so it's the mx, but we also want the coefficient of the c. So in order to get the coefficient of the c, I have to generate a basis which is got all the x data, and then for every value it's also got a 1 corresponding to how we can calculate the constant. So what we do, and you will have to play around with this a bit yourselves, I'm generating my linear basis with all the x data, and then for every data point there's also a corresponding 1, so I can actually match it up and calculate the coefficient which corresponds to the offset. I then use regress. You have to pass it to the regress function. You have to make sure you get the dimensions the right way round. That's why I've got these transpose in there. Play around with it yourself and you'll find out how to do that. And then basically what you've got to do is, after you've done the regress function, it returns in BS, in one of the, it's got multiple options of returning things. It returns the values for the coefficients. So the first coefficient and the second coefficient. First coefficient is actually the coefficient for the first term here, which is going to be effectively our m, and the second one's going to be for the constant term is going to be our c. And then all I'm doing is I'm actually generating the predicted line again, and I'm just plotting the x and the y data. I'm plotting our fitted line. Now in this case we can't fit a straight line to this, right? We can't do it because it's not a straight line, it's a curve. But it will do the best it can. It's doing, it's finding the best line which minimises the summed squared error, right? That's what it's doing, and it's what it's done over that range. Now, like I said, you can't actually fit that line very well because it's not actually a straight line that we need. But what we can do is something called the kernel trick. So we can actually put another basis in, and the idea of the kernel trick is we can transform some data in such a way that we can make it, if you like, easier to process. So one example might be, imagine we're representing data in an x and y fashion like this. We've got all the x data here and all the y data here, and this would be like plotting positions in Cartesian space of two different classes of data, right? Now, looking at that, there's no way we can actually classify this with a linear classifier. But what we can do is we could do a polar representation of this data, right? What we can do around some point, and in fact it's going to be around the center points here, and then we could do a polar representation there's an R, a radius point from the origin, and there's also an angle from the origin. And if we change the way we represent the data effectively. If we represent the data in a different way, what we can do is we can plot in polar terms in such a way that we can see actually now the data looks as it's actually quite separate and something that we could actually chop up using a linear function, right? So basically a kernel is a sort of a mapping function that transforms one space into another. And we can use this to our advantage in this case by saying, well, rather than trying to fit a line to it, which is just a linear line, we can represent the data with a different, more complicated basis function, which is quadratic. So I'm going to generate a quadratic basis function. So I've got x dot times x. So basically this is the squared value of all the x values. Then we've got all the x values. Then we've got a constant. And what this will do, if we then do this and we use this this quadratic base, we end up with three values coming out. Of course, the fitted values for the squared term, the fitted values for the linear term, the fitted values for the constant term. What it'll let us do is then actually fit, in this case, a quadratic curve to the data. So we're doing actually a linear fit with linear regression, but we're using this basis which actually transforms the data. So that's a nice little thing to bear in mind when you're doing this kind of work. Just as a last preview of the next stuff, let's think about how easy it is actually to do this in Matlab if you're using a vectorized representation of the data. In fact, you're not limited to a single dimension. We can have multi-dimensional regression, and the closed form solution is actually quite simple. It's if we got the data value, the x values in a vector x, and the y values in a vector y, the weight vector that we end up with, which is effectively going to be if we do it in a one-dimensional case, it will give us the m and the x, the m and the c. All we have to calculate is x transpose x. We take the inverse and we multiply it by x transpose y, right? And in Matlab, it would be done using the following simple line. This is doing linear regression, multidimensional. In the multidimensional case, and what we do is we calculate x transpose x. So we got the data vector x. We transpose it and multiply it by itself. We take the inverse and we multiply it by x transpose y, and that in one single go will generate the solution to your linear regression problem. And we'll talk a lot about that when we talk about vectorized linear regression solutions.